Hey everyone, so my name is Paul. I'm the founder of Somnia, and I'm going to be talking about what Somnia is and how we enable real-time applications on the EVM. I used to work at a company called Improbable. You may have heard of Improbable. So we basically built gaming and metaverse technology designed to scale up to thousands of people in the same space at the same time. So this is used across different metaverses. So people like Major League Baseball use this to do digital baseball games. People like Yuga Labs use this to build Otherside. And there's also music events, people doing like K-pop, those kind of events. Now the vision here really was to make a digital asset economy where anyone buying an item was ultimately buying an NFT behind the scenes. That was the vision behind it. The problem we faced was when you actually look to put every single item in these experiences on a blockchain, the existing chains in the market didn't scale to that level. We kept trying lots of different things and trying lots of different Web 2 caching layers, but ultimately we felt, okay, we need to solve this problem of how do we enable high-scale throughput applications on top of the EVM. So that's kind of where this came from. So that's what Somnia is. So basically, it's a high-performance L1 for the EVM. First thing is the transaction throughput. So it runs at 300,000 transactions per second, maybe 400,000, depending if it's a good day. It also is very low latency. So whenever you submit a transaction, the finality is less than 1 second. That's very important for these real-time style applications, which enable this kind of high performance and low latency applications. The next thing is EVM based. So this was very important for us. When we were looking at chains in the market at the time, there were other chains that existed that were outside of the EVM that could have hit the scale requirements we needed. But we felt it was very important to build on top of an ecosystem that already had a load of tooling and a load of developers and a load of assets. So that's why we made sure that this was based on top of the EVM. So you can bring in any Solidity code you've written before, deploy that onto Somnia, and it will scale. The final thing was low cost. So when you're looking at these kind of gaming and metaverse style applications, you're looking at items that cost $1 or less, and you really need to think through how you make your gas costs sub-cent. And so this was another kind of design principle, the fact that you can now have gas fees that are below 1 cent, so you can do micro-style transactions. But the vision we really want to push to is moving a lot more logic that used to live off-chain, on-chain. And that means you can have fully on-chain applications, like on-chain games, on-chain social media, and with that high performance that I talked about before, this now becomes a possibility. So that's what Somnia is at high level. Now, I'm going to go through today how we do that. I'm not going to go through it in loads of detail, but I'm going to go for a high level. So there's 4 main innovations that we've kind of done. The first is execution optimization, so making a single EVM thread run faster. The second is a new consensus mechanism that enables for high throughput and lower latency applications. The third thing is much better compression for node-to-node communication. I think this is one of the biggest problems when you're getting to these transaction levels that people don't really talk about in the space, and I'll go through this in more detail. And the final thing is a new custom database that enables more predictable pricing and faster and read writes. So these 4 things are what I'm going to go through today. So the first thing is execution. So this I'm going to frame the problem up. So a lot of approaches in the market today are looking at parallel approaches, where you have essentially multiple threads, each doing transactions and each processing things. This works very well when those threads are not touching the same piece of state. So if we're doing a swap between 2 wallets, if another wallet over here is interacting with a smart contract and minting an NFT, if another wallet is doing a DEX swap, and these are all not touching the same piece of state or going through the same piece of code, parallel works very well and can scale very well. The problem is when everything is interacting with the same thing at the same time. So when you have hundreds, thousands of wallets all interacting with the same piece of state and the same smart contract, parallel doesn't scale. Now, people who are making parallel EVMs will say, well, we just roll back the transaction, run it sequentially, and it's fine. But if you have users continually hammering the same thing over and over again, like you do in real-time applications, it won't work, and you'll end up running a slower sequential EVM. So people are like, well, this never happens. But this is exactly what happened in the Otherside mint. It's one of the biggest events in Ethereum's history. You had tens of thousands of people all trying to mint the same NFT at the same time, and a parallel approach wouldn't have scaled that properly. This is why we believe you need a faster sequential approach. So this meme goes around the company quite a lot. We call it EVM go burr. That's what everyone says internally. There's loads of smart stuff that goes into making a parallel EVM. What we've done is very much a left curve approach of just making the EVM go faster. So how have we done that? The first thing is compiled bytecode. So this takes advantage of hardware parallelism. So modern CPU architectures, as you all know, are very, very good at parallelizing things once you're running compiled code. But most of the time, most blockchains on the market interpret EVM code and run that. So we basically compile down the EVM code at runtime, which turns it to x86, and that means it can be run on top of CPUs in a hardware parallelized way. So this is much faster than if you're just interpreting code. The other nice thing here is we don't affect the developer workflow too much because this is happening once you upload the code into the blockchain. It's not being done at the time when you're actually developing the code. So that enables hardware parallelization. We use this a lot in the games industry, and not a lot of people talk about it in other industries, but we used it a lot. For years, we just wrote single-threaded code and didn't use parallel architectures for a long, long time. So the next thing is the database, and I want to kind of frame up the problem here with a question. So when you're reading from a database, that is very unpredictable. You don't know if you're hitting memory, if you're hitting disk, and so therefore you don't really know the cost. And so the question is, how much gas should you charge for when you're interacting with a blockchain? And I think the answer is you kind of have to go for the most degenerate case, always assuming that you're going to hit disk and charge the most amount of gas on a per transaction basis. Now this causes a problem because you're always charging a maximum amount of gas, so you can't fit as much gas as you could into a singular block. So what if you could predict the cost of a read or a write before you did it? So that's why we made our own custom database called IceDB. This is a ChatGPT image, which does two things basically: make the costs of read or writes much more predictable, and also make them much faster. So how do we do that? So the predictability and understandability is probably a better word, comes from this concept we call performance reports. So every time you're doing a read or write in IceDB, a performance report is created associated with it. So what we do is basically track if you're hitting cache, if you're hitting disk, a performance report is created that is shuttled back so we can work out the exact cost of that read or write. That means we can charge the exact right amount of gas for each read and write, and therefore we can fit more gas into each block, and therefore more transactions. So performance reports, the first thing. The next thing, I was going to go into a lot more detail here, but I kind of kept it short. We created a custom read-write cache, LRU caching mechanism, that is super fast. It allows for read or writes of 70 to 100 nanoseconds. We looked at other databases that exist in the market today, LevelsDB, RocksDB, and we found there was lots of problems in the implementation in terms of their caching strategy. So we invented a new one. I say invented a new one, made a new one, and that makes reading and writing significantly faster than most blockchains on the market today. So that's IceDB, our new database. So now we have a single-threaded application that runs fast and a much faster database. The next is consensus. So the consensus mechanism we've gone with, we thought we created, but it's actually inspired by this white paper called Motorway BFTP. So the way this works is each validator runs what we call its own data chain. You can think of it as its own blockchain where it's creating its own blocks. So basically each validator can run as fast as it can, creating its own blocks up and up and up. Every 10 to 20 milliseconds, there is a global consensus chain that runs across all of these validators, creating the head of the blockchain. So we're constantly running this consensus chain over and over again, creating a new head state. Each validator is continually reading from this to work out what is the current state to make sure it's got the most up-to-date state. So this means that validators can run super duper fast because they don't have to always wait for that global consensus to happen. That happens as and when it can, keeping up with the chain. The problem with this architecture is your chain can only run really as fast as your slowest validator. So if you have a really slow validator, this creates much more of a slowdown in the blockchain architecture. So that means that we do have minimum hardware requirements for our blockchain. So we have traded off a bit of decentralization for this increased performance, but we think it's well worth it. It's still much better than a very centralized blockchain, but in current tests, we're running across 100 nodes with a node similar size to what you see on Solana or Aptos. So that's the consensus algorithm. It essentially enables much higher throughput, much lower latency. So the big problem, and this problem isn't really talked about a lot. I don't really know why. When you're running at these transaction levels, you're making a lot of data. So if you think about each Ethereum transaction is about 200 bytes. If you're running at 1 million transactions per second, that's 190 megabytes per second or 1.5 gigabits. That is not very good if you're running that across the public internet. So you really need to think about how you take that data and compress it down to be much smaller so that nodes can communicate with each other more effectively. So that's what we've really thought about. We use similar techniques that I showed at the top slide with that high-scale multiplayer technology, and we kind of applied that to blockchains. So let me go into a little bit more detail on how that works. So the first thing is we take advantage of a power law. So if you look at how Ethereum transactions are distributed, it's a power law, with around 10% of transactions being called 90%, 10% of contracts and state being called 90% of the time. So because you have this parallel distribution, you can take advantage of that and compress down the data of those contracts and those things that are being accessed over and over again and get a much better compression ratio than normal. These power laws exist everywhere. Internet traffic is distributed like this. Game sales are distributed like this. Anywhere where there's a network, you really see this power law, and you can exploit this with a compression algorithm. So that's the first thing. The second thing is we use streaming compression. So streaming compression gives you much better compression ratios than other compression techniques. I'll explain what most people use. So most of the time, people use block-based compression. So block-based compression is used in image, but it's also used in blockchains. The way this works is you take all of the data that exists and compress that down. Because you have total information, you can send that over to someone else, and that can be decompressed. So that works very well for images, very good for files. But we use streaming compression. So this is what's used in videos. The way this works is you reference previous frames, in our case, previous blocks, and take data from that and reference data from that, giving you significantly better compression ratios, because you don't have to just take all the data, compress it down, and send it over. You can reference previous blocks in the streams, which gives you much better compression ratios than block-based compression. Fun fact I found out, a lot of blockchains don't even compress data. They just send full Merkle trees around, because they don't really need to, because the transaction throughput's not that high. But anyway, streaming compression, that's the next thing. The final thing is signatures. So this one's a big one. Signatures are by definition uncompressible. So what we do is essentially batch them together and then process them in batches. So this is using a BLS signature scheme. This is actually used a lot in blockchain, but normally is only used between validator nodes. So if you look at the beacon chain in Ethereum, that uses a BLS signature scheme. We use this across everything in the stack. So whether an account is, a wallet is interacting or a validator is interacting, it's all using the BLS signature scheme. We also have a transaction batching method which enables this to be possible. Now we are still compatible with traditional Ethereum transactions, so you can use your old wallets. It just runs in a slightly slower mode. So we have two runtime modes. One is BLS signatures, one is elliptical curve, in case you still want to use your classic MetaMask wallet. So the novel compression algorithm based on the power law, streaming compression, plus signature batching, plus a bunch of other stuff, gives significantly better compression ratios, 10 to 20 times better than most other chains that exist, meaning we can have much higher transaction throughput, compress that data down, and synchronize that across the nodes. So those are the four things that I want to talk about today. How we make Somnia fast and how we enable it to scale for real-time applications. 1, improved single-threaded execution. 2, a new database allowing faster read and writes and more predictable read and writes. 3, a new consensus algorithm that enables higher throughput and lower latency through those data chains and that global consensus chain. And 4, novel compression algorithms that enable 10 to 20 times better compression ratios than exist today. So where we are with all of this is our DevNet is going to be launching in November. So we're now starting to want to talk to developers who are interested in building applications for the chain. We're particularly interested in people who are building on-chain games, people who are also building real-time social file applications, or maybe a DeFi application that needs to scale to millions of users. So talking about the DevNet in November, testnet will be early next year, mainnet will be end of H1 next year.